Okay, class, we're back to oxygen loading in the blood. We've had an extensive talk on the oxygen dissociation curve, so we're going to apply all of this now. All right, oxygen carried in the blood in two ways. We already said hemoglobin and the dissolved. Okay, it's carried on the iron in the +2 oxidation state. 1 gram can carry between 1.32 1.39. We said about an average of 1.34. So what we've done is we've talked about loading here. And then we really have talked about unloading using the curve. Okay, so here's how the thing would go. Let's start up here first. Up here, oxygen loads in, right? Up here, the CO2 level is low. So that means if that is the case with a low CO2 level, then it facilitates loading when we get to the oxygen dissociation curve. Why? Because what will happen is the curve then would shift to this direction. Remember, if with decreased CO2, you go this direction. So that's good, because it's up here that you want to load, and the CO2 level up here, the PaCO2 level up in here would be low, because this is where you are blowing it off. See, that PaCO2 is around 40. So you'd shift to facilitate the loading of O2. All right. Then when we get down here, okay, so we've loaded. Let me just say we've loaded. Then we come over here, and then we'll get down here. All right. So then how do you increase blood oxygen carry up here? Let's say, how do you increase your carrying of blood oxygen? I'm gonna do that in terms of hemoglobin. So these are putting practical points to this. In terms of hemoglobin, have more hemoglobin. Normal hemoglobin was 12 to 16. The higher you have, the better. Up to a point. Because if you got more hemoglobin, you got more red blood cells. Now remember, the hematocrit is the percentage of formed elements. If we get too high of a crit or too many red blood cells, it increases too much viscosity, which could cause blood clots. Remember, that's what I said. Some people that have polycythemia again was too many red blood cells. Polycythemia, then that's where the barber used to be. He used to bloodlet using leeches. Okay? So up to a point you can get a better oxygenation, but there are other problems associated if you start getting too high. The other thing is to hope that you got a lot of iron in the +2, which means eliminate some free radicals. Antioxidants. What did I just say? Antioxidants. Eliminate some of those free radicals that convert the +2 to the +3. Now, that's the hemoglobin part. You remember 97% to 98% is carried on hemoglobin, right? That's what we just said. How do you increase the dissolved fraction? Well, you can't change the solubility coefficient for oxygen. That's set in the chemistry of it. But what you could do is increase the atmospheric pressure, Henry's law. The amount of gas that will dissolve in a liquid depends on the partial pressure of the gas above the liquid. How do you increase the partial pressure? Increase the atmospheric pressure, the total. You could take it to 2 atms or 3 atms atmospheric pressure. Where do you do that? Like in the hyperbaric chamber. What's the reason for increasing oxygenation in the tissues? Well, when you get into micro, certain organisms like the Clostridium group, the Clostridium welchi, the Clostridium tetani, those don't like oxygen. As a matter of fact, oxygen can kill them. Okay? The perfringens bacteria. So if you drive more oxygen in the tissues up to a point, then it can kill those. Okay? Now, what is the problem with that? The problem is if you drive too much, so I'm going to come down here if I can find it real quick. You drive too much oxygen in the tissues. That's just because, you know, as I've told you many times, too much can be bad. Too little is bad and too much is bad. Okay, these are hypoxia deals. I'm not ready for that. That's hypoxia. We're going to talk about that in a minute. But right now, I'm talking about hyperoxia, putting too much oxygen in the tissues. If you are an adult, it can cause something called bronchopulmonary dysplasia. So too much. It's a chronic lung disorder that's more common among children who were born with low birth weights. But in the adult, what it basically is it thickens the alveoli and can cause fibrosis. Okay. Now, if you are preemie and you put too much, it can actually burn out the eyes. Retrolental fibroplasia, an eye disease with too much oxygenation. So too much oxygen ain't good either. Then too little is not good either. And we're going to talk about in a moment hypoxia conditions, but I'm not ready right now. All right. So we go back and you picked up your oxygen, right? You picked up your oxygen. So now you're going to carry it and you're going to unload it. Okay? Now when you get ready to unload it, remember you have some attached to hemoglobin and some dissolved. Well, if you think of the red blood cell and you think of the bloodstream, let's say, the first amount, I'm going to come here, let's say we're down in the tissues. The first amount is going to come from the dissolved. So when you lose one from the dissolved, hemoglobin will lose one. See, hemoglobin has more affinity. If I compare the dissolved amount to that on hemoglobin, the dissolved amount has less affinity. Now, an example of that. If I were to oxygenate water, let's say I took water and just pumped oxygen into water, you'd see it bubble, just like you do with a Coke, but that's CO2. So we're going to say that the oxygen in the solution, in the plasma, is in a volatile form, just as if I oxygenate water, you know, like in your fish tank at home, if you got one. You're oxygenating the water. It's bubbling. So the first molecule of oxygen would come from the plasma, because it's the most volatile. Then, now remember Henry's law, you have the plasma saturated. So when one comes from the plasma, that's going to allow one to come from the hemoglobin. So you unload first, if we're unloading, from that. Now, when we were loading, however, since hemoglobin has the greatest affinity, when you unload a bunch of O2s, when you put it from the alveoli, the hemoglobin gobbles them up, and whatever's left over while the blood is still in that position will go to the plasma. So on loading, hemoglobin gets the first share, loads itself up, and then what's left over goes to the plasma. But on unloading, exactly the same, because you got the volatile component in the plasma with the least affinity. So the first molecules come off of that, and then hemoglobin unloads later. So now what will have happened if everything's going right, you would have unloaded into the tissue and come back around. So you came in, let's say a 103, 104, 102, unloaded, came back around, and now you got a 40, and now you want to go on back around and pick up again. Go on back around and pick up again. So that's essentially how it goes. I think we've explained the crux of this deal, and you can read on it. I've taken plenty of time to do that. Okay, so let's go further now. Let's go further. We talked about the dissociation curve and everything like that, the shifting and everything. We talked about loading and unloading. All right. So now what I want to do, I want to get into this discussion, and I'm going to start a new video. This is going to be on hypoxia. Remember, that's one of the talks we would do. We already talked about hyperoxia. So this is where we're going to start now. I'm going to close this one out and start there.